Hey, my name is Mikhail Sergachev. I work for JIC, the Joint Institute for Computational Sciences, and today we are going to continue our discussion of programming with MPI. Last time, on Thursday, we talked about message passing interface in general, and then also talked about point-to-point communication. And I promised that today we'll be talking about collective communications and derived data types. And it looks like we might have time to talk about it as well, and MPI two sections as well. We're talking about collective communication. So last time, point-to-point communication involves message passing between and only two MPI stacks. Well, collective communication, these calls are basically the substitutes for a more complex sequence of point-to-point calls. As opposed to point-to-point communication, collective communication involves multiple processes, and all of these processes have to be in the same process group. And they have to be called by all processes are called in the same communicator. That's the universe for the MPI. That's what we call the universe for the MPI collective call. So during all MPI collective routines are blocking. So block until locally complete, but with MPI-free standard, collective operations can also be unblocked. But the purposes of this talk will only assume that the collective call is blocked. And some of the restrictions or programming hints. So the buffers for collective calls must be exactly the same, basically, as opposed to point-to-point, no message tags that are needed or required, and that MPI collective calls can only be used with MPI predefined data types. A little about, the data types today. So generally, three types of collective operations or functionalities. So synchronization is one of the functionalities that collective operations offer. And what it really does is it syncs the processes, meaning that processes will wait until all members of the group reach a certain synchronization point. The second functionality is, of course, data movement. So we are passing, sending, and receiving messages using MPI collective calls, just like we did with point-to-point. But two processes can be involved in communication. The type is global computation, which is again sending messages. Only one member of the group collects the data from the other member and performs a certain mathematical operation or a function data. So this will saves programming time as well as data movement and basic collective communication calls. So let's talk about the synchronization part of collective call functionality. And MPI defines a routine called MPI barrier, and it is pretty explanatory. It synchronizes all processes within a communicator. So specify a communicator when you call MPI barrier function as shown here in the sync part of the slide. So basically, the idea is that no processes in the communicator can have the barrier until all of them call the function. MPI function. And schematic, how, for instance, the error are pointing from left to right, indicating the execution time, the runtime, and you see that at some time T1, the processes are synchronized, and once 0 hits the error, it stops and waits for other 3 processes to reach this point. Looks like time T2, processor 1 and 3 reach the same point, so they also stop and wait for the remaining process 2 to reach the point. Once they all reach this exact same point, once they all execute this MPI function, they're allowed to proceed. And this is how it works. And all I wanted to mention about the synchronization part area is pretty standard function. So there are several data movement routines that we'll talk about. The first one is MPI broadcast, and let some process broadcast or send a message to all other processes within the indicator again. DCAP, MPI underscore DCAP is the name of the function, and as all other communication routines, it must be called each node in the group, each task in the group. This illustration, we see that the root process, we make a process, we rank 0 to be the root process in the MPI broadcast function, and what is it gives a message of certain size down of size type to all of their processes. And for this example, we're using 8 processes, so we're assuming that there's 8 processes in the community. And this example would be 0. So this is for the MPI function. Pretty straightforward, very easy. And if you think about it, only thing is when root process 0 called MPI task, what it does is it replaces it with a from 1 to 7 and broadcast usually by MPI send. So on the side, MPI broadcast is really MPI send to all the processes in the indicator, and on the receive or on the side of processes 1 through 7, MPI decast is replaced by MPI receive. So, you can write a simple, maybe 5 lines to replace the MPI decast yourself, just MPI send and receive. I mentioned using elective call saves not only time, programming time, but MPI will actually generally will make it more efficient and buffer the best possible way. So everyone understands to use elective calls. That's what your algorithm is allowing. Function MPI data movement function is MPI scatter. So what does it distributes distance messages from one process to all other processes in the group. So the difference between MPI broadcast and MPI scatter is that instead of distributing one contiguous chunk to all processes, it actually splits up the data. The root splits up the data and sends equalized chunks to the remaining processes in the communicator. So, for example, we have the designated root process is process 3, and it has an integer. Yes, it's an integer. An integer array of 12, and what it does, it splits it up in equal chunks of 2 integers and sends it to process 0, 1, 2, 3, 4, and 5. So in the receive buffer on each of the processes will only have 2 integers. And for instance, process 2, 5, and 6, and the 4 have 9 and 10. And process 3 will send itself a chunk of data as well, and will basically get back 7 and 8 scatter works. Again, if there is an MPI scatter, there should be an MPI gather, and there is indeed a function called MPI gather, and this illustrates how a array that resides in process 0 will be across processes indicator, and vice versa, how process 0, rank 0 would gather equal chunks from all of the different processes in the communicator in its own receive buffer. It is, as always, a vector. So it's any other. So it gathers distinct messages from each processes in the group. The same process in the order of processing. What did we do? So this is basically a reverse optimization of MPI, and it can show how processes in the communicator have equal size, 2 integer size arrays, and MPI gather function will make sure that all of these processes send to a single root process, which in this case again process 3, and the receive buffer for process 3 will have all of the 12. Very straightforward. I'm not spending too much time on this. Pretty easy. Scatter D and MPI gather D are basically same MPI scatter and gather, but allow varying counts of data and flexibility for data placement. So see that there is an extra argument here displayed and an array of displacement. So now you can actually in a non-contiguous fashion. Before all of this chunks were in a contiguous array or root process 3, well, we gather they have gaps in between. The question is MPI gather. What it does is concatenates data to all tasks in the group. So again, each task right here, processes 0 through 5 have of data, and all gather function will basically roll out this of the process. So what it actually does is it gathers first and gathers all of the data on some high process, and then broadcasts that data across all of the process. So again, you can even mimic the behavior of all gather by using 2 functions, MPI gather and MPI broadcast. Once again, all of this is for the program to simplify your effort in writing that. And these functions are most part guaranteed to work well efficient most applications. MPI all-to-all would probably be the most expensive function mentioned so far. So it sends data from all processes to all processes. Let's actually start here and talk about. So we just have a send buffer. So you have to specify, well, for D language, you specify a pointer to data start. Have to specify the number of elements sent to each process. That's S count. Always specify the data, and this can be the predefined data type, from what I understand. Of the receive buffer, that's again a pointer to the number of the receive count is the number of elements received from any process, and the type the receive buffer has to be specified as well. And for all MPI collected calls, for the most part, you use MPI on all. We'll talk about these. So this is the behavior of an MPI all-to-all function. So if, let's say, I have 5 processes, and each process has its own array of either integers or doubles or what have you. As you can see, all of these arrays are different. What MPI all-to-all function does, mathematically speaking, so the range of the process is the J in the array. So you have process A and entry 1 equals to entry 0, then it goes to process 0, entry 5. Yeah, so what it's basically doing is a transposition. If you think about it as a matrix, and transposes the data. You can see, process 0 will only receive section of each process is erased. Process will receive the second, and so forth. So that's fine. So let's talk about the computation routines. So it allows you to perform mathematical operations with data that resides on multiple processes. So the process of the group is collect the data from all the other processes first to perform the operation. Minimum, maximum, what happens. In fact, a lot of these MPI reduction operations are predefined. So some product, maximum, minimum. So MPI allows you to define your own reductions by using the MPI of create routine. Functionalities there, we'll talk about it, but let's at least mention some of the predefined reduction operations. So a function that would find a maximum value of all values that reside on the processes within the communicator is MPI underscore max. So M finds minimum, MPI sum will sum the lot, etc. So there's a few of them that were predefined by the MPI standard. But once you can write your own function using MPI of. So how would you do the reduction, how would you implement it in the code? So the tools that are used to do that are called MPI underscore use and underscore all. And those that for the reduce MPI reduce operation must specify the root operation because MPI reduce will resolve only to one task, that root task that is specified. And MPI all reduce doesn't be redundant because once the is computed, it is returned to all of the tasks. So no root process is necessary. So highlighted it. That only applies to MPI review. The extra argument. So well, let me just mention here that the operation, this I showed you apply inside max and min. This is the place where you will put the communicator for the employee reduce environment for the reduce. So an example of MPI reduce and MPI all reduce, where we have 4 processes and each process has a single integer equal to basically the root, the rank of the process plus 1. So process 0, 1, 2, and 3 will contain numbers 1, 2, 3, and 4. So that's same on the right side where also operate. Again, for reduce, we have to specify the root process. So let's say it is process 0. So this is end buffer. So that's what we have before the MPI reduce or MPI all reduce function is called. So 1, 2, 3, 4, 1, 2, 3, 4. Once we call this function and we use MPI sum operation, receiver for after the MPI reduce function is called will be equal to 10, is that 1 plus 2 plus 3 plus 4, and it will be stored on the root process home and designated process 2 or process. The receive buffers or processes 0, 1, and 2 will be undefined or the exact same value. I already used that result, the sum 1 plus 2 plus 3 plus 4 will actually be both processes. So pretty and very, very good functionality. A lot of codes actually exploit it. It's very. Let's stop talking about collective communication and move on to derived data types. So in the presentation on today, I showed you slides where I showed the basic MPI data types, which are previous data types. And this is particular, this table applies to the C language, but for Fortran, it's pretty much the same. So all of the previous data types start with MPI underscore, just like MPI entity, and then for you would use capitalized char, int, long flow, etc. So the type part is capitalized. So these are names. Well, in these basic data types, MPI allows you to define, or as we say, derive your own data structure based on sequences of the MPI basic data types. Or you can actually use derive types to derive an even higher level of data types. So you can derive data types to derive other data types, or with only the basic MPI data types. So the main reason why you want to use it is to be able to, and a good way of communicating types or non-contiguous types in a single map. Otherwise, how would you a map that has different types in the same array, so to speak, use data types. So you have to have your own data types and send them, and in the MPI send and receive function. One of the main usages of this is MPI I/O. Different fields have different data layouts in memory, and and different layouts in the file itself. So to map it, you would want to create data types in order to be able to do the efficiently. So I mentioned is data types are created with one time through calls to MPI library. So you can create them and destroy them during time. MPI provides several methods for constructing derived data types. So there's contiguous, vector, index, and now I'll talk about each of these four data types. Derived types. So this is called MPI type contiguous, and this is the sys this. So what it produces a new data type by making counties of an existing data type. We call it old type. So you have, for instance, 10. Count is an old type in, then type, which you'll save in the new type with the new type variable will have integers. That will be considered as a single entity. So then if you send if you entity of a new type using MPI extend, the send receive better have integers in it. Otherwise, you won't be sending enough data in the MPI send function. So one single entity will have 10 integers. And this is not very useful because you can always use MPI extend, and instead of specifying the buffer size of 1, you can specify the buffer size of 10. And instead of using this fancy new type derived data type, you can just use basic MPI integer. The reason this derived type exists is because you can use it when you construct, more complex with, say, using MPI type index or MPI type struct. As I already mentioned, MPI data types can be created using previously created MPI derived data types. So, for the gibberish, but that's I think a pretty way of explaining why one wants to use MPI type contiguous data type. MPI type vector is very similar to contiguous, but it's regular gaps between the data. So see, we have an extra arg the MPI type vector, it's called stride, as well as the length. So these specify the number of elements, and try to find the offset between those elements. So if it is bigger than the size of one block here, they have a gap. And MPI type vector like to do. But these are uniform or regular. There might be a limitation for certain applications. So to fix that, there is another type called MPI type index, which is again an extension of MPI vector, but it allows you to have multiple block lengths and or offset. So a length here is just a number, so it can be 3, 4, it's an integer, and the size is again a positive integer. If the length and stripe is replaced with an array of varying block length and offset. An even more general type, the MPI type stripe, which actually allows you to have varying types of data. So you see that there's old type everywhere, and up to this point, there's only one type that could be specified, the MPI previous vector index function. But with struct, you have different data types, different blocks, and that's what's highlighted here in color. And that you can have, so for instance, this red section could be MPI contiguous, specified the MPI function. And this, well, yeah, so we've got the idea. So let's look at an example where we use an MPI type vector function. Once again, the type which allows for regular gaps in between blocks. So we have a matrix that is 4 by 4 with 1, 2, 3, and 4 as floats in the row, and the second has 5, 6, it should be 7, 8, and let's say that we've specified the count, the variable to be 4, so count is 4, and one count is the number of blocks. It has to be a non-negative integer. So if this is 4, the name is 1, so we put 1 in here. This 4, block is the number of elements in each block. So block B contains single integer. 4 integers. Okay, now let's continue. So try is 4 in our example. So the number of elements between the start of each block is 4. And of course, we have to specify the type, the original type of A, which as you can see is float. MPI float will go right in here, and then we'll come up with some name, and let's call it new type. Let's go that will actually extract the column from the by using derived data. And one send operation, it will actually extract all 4 numbers from this matrix and send you some product. So we have again a matrix of 4 by 4 by matrix of type float, we have to specify the destination. Um, and with that, first a new type is type MPI data type. So once we call this function MPI type vector with count for block length of 1, try of 4, MPI new type, create a new data type that, if applied to matrix A, will extract exactly the second column matrix. So you'll get 2, 6, 10, and 14. And the reason it does it is because we see that the count is 4. So the block is of size 4. So we the row will fit perfectly in the first block. Pressing the button. The length is 1, so we extract one variable, but how often? Every that well, I need to specify the starting location with our stand operation. So if at 1, which is this entry right here, that will extract the first entry, then skip 1, 2, 3, 4, and track the next one. So fourth entry. So I type vector, first entry, then skip some, say 3 floats in our case, then 5th entry, then 3 more. So it's doing here. So if your address is this entry right here, so then we'll extract every fourth variable entry. And again, matrix given by 4, we know that a numerator is stored as linear sequence, right? So how you would use an MPI type vector functionality type that can extract a column, or you can do the same thing with rows of a matrix. Again, this column becomes just one element of type new type. You see we are sending this one single element of type new type. Okay, and with template destinations that we have defined. Okay, so that's what I have for API-derived data types. Let's now talk about communicator. I keep saying that you're sending messages to the communicator, and for collective calls in particular, they have to share the same communicator when they're executed by the process in that group. So, last time we had, AI uses objects called communicators and groups, find which collection of processes may communicate with each other. API communication calls require a communicator argument, as we will always see. It's always as the last argument C and on port. All of the MPI processes can communicate. The input process can only communicate with a communicator. Point to point or collective. What helps you define the communication. So I initialize the default communicator called MPI called world, and as also that's the communicator that probably using for the most part. And of course, the base group, the icon world, contains all processes. So base group is So for instance, this example right here, we have this, so we run our code, we main process it. So we process it, will be part of the MPI world communicator. So we have a group, the base group of size 8. So what does do for you? If you wanted to create your own groups and communicators, what would it allow you to do as a program? So it will to organize tasks based upon application nature into task groups. Applications, so when you implement libraries, you want to allocate a certain group of processes that will do a certain part, certain task in your code. Functionality also allows you to enable collective communication across the subset of the related tasks. As you do in like MPI broadcast to only 4 processes out of 8. Well, if you find a smaller group, 4 processes and associate a communicator, you have to come up with a name for the communicator as well. But that communicator name that you'll use in your MPI broadcast. And also, create your own groups and communicators will allow you to implement virtual communication topologies, which I'll show in a couple of minutes. So guys, they order of an order process. Each is in a group is associated with a unique rank. We talked about that last time. So the ranks are always start at 0 and they go to n-1 in both and team. And one process can actually belong to 2 or more groups. So start with the base group of say 8 processes and set up multiple groups. One process can have multiple ranges being in different fields. An example. And as far as MPI communicators are concerned, they determine the scope and the communication universe, and each contains a group of valid participants. So that's obvious. And data types, groups of communicators are dynamic objects, and they can be created and destroyed during the runtime. So here's an example, an application that uses 8 processes, and of course, all of the 8 processes will MPI on the wall mediator. So the base group is 8, and the table should have really been one long table of 3 by 8. By 8, but since it doesn't fit this slide, I use the color. So we see that in MPI home world, blue color, the ranks of say process 0, all ranges are all ranges range from 0 to 7 basically, and if we split this group into 2 parts, so we have group 1 and group 2, and say put processes 0, 3, and 4 in group 1 and processes 2, 7, 5, and 4 in group 2, then when we create a new communicator, this will be assigned different ranks. Again, starting from 0 to 3, 0, 1 to 3, and these 4 processes will do the exact same thing. So they will get new ranks from 0 to 3. So look at this version. So we are 0, or let's be different. Let's pick this one. 3 originally in AI home world became 1 in communicator 1, you can see it here, and can even be split even further. So the process in MPI on world communicator will become ranked in communicator called COM5. So this is how it goes. So every process has 3 communicating groups and a distinct rank associated to it. So each process has different ranks. There's over 40 functions that MPI standard by for communicators as well as virtual topology. But the usage for creating your own groups and communicators is as follows. First of all, you handle a global group from MPI COM world. So you use MPI COM group function, use MPI COM world, and you'll learn to handle the base communicator, the default communicator. You form new group as a subset of global group using MPI group included. So that's the function that will actually the splitting of the base group into say 2 parts, as an example. Communicator for the new, and you use that COM create. So that's how you can get COM1 and COM2. And do, of course, do the same MPI COM range, the same function that we talked about last time to determine new ranks in the communicator, and to start sending messages in either point-to-point calls or collective calls. And when done, you free out the communicator using MPI COM3, and you free out the group using MPI group 3. So that's, like I said, these are dynamic entities of API in the runtime. And the virtual topologists are used, like communicators and groups, and they describe a mapping of MPI processes into genetic state. So for some applications, for instance, if they have a Cartesian topology or Cartesian map, so sometimes if you give a domain into equal chunks, like it is shown in this slide, and assign it to processes 0-3 contiguously, then it is because that process 0 will have to communicate with adjacent processes 1 and 4, or process 5 will communicate with adjacent processes 1, 9, 4, and 6. So to this, to program this behavior much quicker and efficiently, use what is called Cartesian virtual topology, where based on your range, you determine the adjacent range of your processes. So 5 in the Cartesian topology will have index 1, 1. So very easy for you to subtract 1 from the first index to get process right above it, or add 1 to the process right below it. So I work with the code that use Cartesian topology, and it's pretty neat. I think it simplifies the programming task a lot. Yeah, of course, we need to calculate the adjacent processes at times it can get more. So I also wanted to talk a little bit about MPI hints and tips. So machine cracking, and I mean, I think it's some environment variables. But let's talk about the trade environment variables that I'm familiar with. So why do we want to use an MPI environment variable? Well, it allows you to tweak optimizations for specific application behavior. So there are internal numbers in every MPI implementation that you should be aware of, especially when you run into some troubles running your code. So you want to be able to see what those values or buffer sizes are and be able to modify them. So plus flexibility to choose product values for collective optimization. I'll talk a little bit about that too. You can, like I said, determine the maximum size of internal MPI resource, buffers, etc. So simply look at what the values are. You will use MPI variables called MPI version display. Will give you the version of trade MPI that you use. But all of the MPI values of all of the MPI variables use called MPI display. You have to set them to 1, about their set to 0. So the second one displays all MPI environment variables and their current values. So output that you will get if you use MPI version display, MPI env display 1, so it displays all of the MPI environment variables. And in the following 2 slides, I'll show you errors that you might get by not properly specified or by using the default values for these 2 MPI variables. So you want to either increase or decrease these sizes to fix errors. If you see this error message, internal abort process 0, blah, 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 and it suggests that you can increase MPI expected buffer size. It says exhaust expected. So what does it mean? Well, it means that the application is sending too many short, unexpected messages to a particular receiver. So what you do to fix this behavior is increase the amount of memory for MPI buffering using MPI unexpected buffer size variable. Previous slide, we saw that this variable is set to 6 megabytes. So use that value, or you can decrease the short message threshold using MPI max short message. Again, the default value is 128. So another is we also have to post the receipt before standard post matching. So technique applies to most MPI installations and implementation. Or you have to be careful using a big system amount of pre-post receipt. Yeah, because you might get into another problem where you would get this kind of error. Well, what you do effectively is you exceed the portal's internal resource limitation. So this each portal other events in this particular case was exceeded. That the default value 248. To increase the size of this key by setting this number to some high value than 2048. So these are examples that I shared with you today. And the last suggestion with a buffers. So you always want to uh, aggregate your buffers that are very small into arrays and then send messages. So you would always want to reduce the number of messages and reduce the buffer size if the buffer size is too small. So for example, all to all, it is definitely, if you have an array of 3 reels, it is better to send it as it with 3 reels rather than sending 3 different calls with one unit number. If you aggregate too much, then I didn't talk about this, but basically, you say that the MPI protocol uses from the stored either route to the long message protocol, and and this link course can be changed within each Mac short message file variable. So you can do that to see it performance. So hints are available on our website. Next UTKDU or next MPI user link to it, so you'll see to learning optimize your code rank back. So, and this was the exact same slide I had on Thursday. Let's some of it use links for you more information about MPI and with some exercises there as well. And some